Hello and welcome to College Algebra 2.4, a library of functions. What it comes down to is we're going to talk about graphs more and more. That most graphs can be summed up with one of these 12 major functions. So we kind of use them in reference. So the first one, excuse me, f of x equals x, or that's the same thing as basically y equals x. And this is, ooh, that's a terrible x. Or that f of x is the same thing as y. Now, if y equals x, then when x is 4, y is 4. When x is 5, y is 5, etc. We call this the identity function because they're the same. And you'll notice it's very linear in nature. We have no restrictions. The domain would be all real numbers, and the range is all real numbers. Here we have the squaring function. F of x equals x squared. Now my domain's unrestricted. However, my range is restricted right at the vertex. So we see that we have a vertex of 0, 2. I never go below that, so my range would be 0 to infinity. Next we have our cubing function. X cubed, left and right forever, up and down forever, no restrictions there. Now we have the square root function. Now the square root function has a fixed endpoint at 0, 0 for its parent because I cannot square root a negative, which means that x has to be greater than or equal to 0. Well, if I plug in 0, because I have this domain restriction in for my function, we get y equals the square root of 0. Y equals 0. We find that 0 is also a fixed endpoint, and that's why the range is also restricted. Here we have what's called the reciprocal function. The reciprocal function is just 1 over x, like a reciprocal of the identity. And of course, we all agree that x cannot equal 0 because it's in the denominator. So we get x equals 0 as a horizontal asymptote. I can never get there. Well, also, interestingly enough, we also get a y equals 0 asymptote. Now this should make sense, but let's take a look at this equation. Y equals 1 over x. If y equals 0, therefore I can just solve for x, but solving this problem, we would multiply both sides by x to get it out of the denominator. 0 times x is 0, 0 equals 1. Naturally, we all agree 0 cannot equal 1, therefore y cannot equal 0. And then, of course, we get our exponential function. Exponential function, where we get a y asymptote at 0, so I'm 0 to infinity in that aspect. The reason that is because e is just some number, and no matter what exponent I have, I will never get to 0. And that can be solved by the same idea. 0 equals e to the x. You can natural log both sides to get rid of the e. And if you type natural log of 0 into your calculator, you get actually an error. So that can't exist either. Therefore, y cannot equal 0. All right, next we get the natural log function. ln of x. So interestingly enough, the domain, well, we just saw that natural log of 0 doesn't work. So the domain is 0 to infinity, and the range is unbounded. So I just want to talk about these for a second. Y equals e to the x, looks like this. And y equals natural log of x, looks like this. Our domain over here was all real numbers, and my range was 0 to infinity for the e to the x function. And over here, my domain was 0 to infinity, and my range was all real numbers. You might notice the domains and ranges flip-flop perfectly. And in fact, these graphs have very similar shapes. One would even say they can be reflected across this y equals x action, or y equals x function. They are inverses of each other. So they are just opposites of each other. They get that reflection. Which makes sense because as we think about it, how did I get rid of this e on this slide? I natural logged both sides. So over here, natural log. If I e'd both sides, it's simplified as well. Here, of course, we get the absolute value function. Absolute value being that I don't get below 0, so my range is 0 to infinity. We, of course, get the sine and cosine function. You'll notice that the ranges are bounded vertically, or both up and bottom. Hopefully this makes sense. Well, let's think about it. If I had y equals cosine of x, well, where does sine come from? Often from triangles. So let's say I have x is this angle right here, and I have a 3, 4, 5 triangle. Excuse me. Well, if I were trying to find cosine of x would be opposite over, adjacent over hypotenuse, 3 over 5. Well, conceptually speaking, what side of the triangle is always going to be the biggest? My hypotenuse. Therefore, the bottom is always going to be bigger than the top. So that sort of eliminates any chances for my range or my y value to be bigger or smaller than 1 and -1. Now what happens is some triangles work out where you get an exact ratio of 1 to 1, but hopefully that makes sense why that's bounded. The same logic would apply for sine. And here we have what's called the greatest integer function. The greatest integer function looks like it fails a vertical line test a whole bunch. Here's how it actually works. You get a closed circle, then an open circle. Then it jumps closed, open, then it jumps closed, open, then it jumps closed, open. Here's also how it works. Let's say x is 3.7777, then the y value is 3. Let's say x is 4.128, y is 4, and let's say x is 3.999999. Y is 3. Y is the greatest integer that you pass until you get to the new one. So, for example, right here, it stays at 0, and then x gets 1, then it jumps up to 1, then it stays at 1 until x gets to 2, then it jumps up. This is also known as the step function. And then here we have the logistic function. The logistic function is bounded at y equals 0 and y equals 1. Okay. Piecewise. Piecewise functions, we're going to graph on our own here. We have two functions. I'm going to use two different colors to represent them. Let's start with this first one. This idea, I'm going to call this one g of x, just for extra labeling, equals x squared when x is less than or equal to 0. We also have h of x equals square root of x plus 1 when x is greater than 0. So when graphing piecewise functions, I would try to get two coordinates along with the coordinate in conflict. So what do I mean by that? The coordinate in conflict here is 0, because 0 shows up for both. So I want to use 0 for both equations. So I'm going to use x equals 0 for this one. And then I want to use two more that qualify. X is less than or equal to 0, so I'm going to use -1 and -2. And then over here, x is greater than 0, so I'm going to use 0, because that's in conflict. I'm going to use 1, but then looking at this, I'm square rooting whatever x value I pick, so I should probably pick x values that have easy square roots. So I'm also going to pick 4. Let's plug it into g of x. We would get 0 squared is 0, so I'm going to get the coordinate 0, 0. We can do -1 squared is 1, so I'm going to get -1, 1. And then -2 squared is 4, so I get -2, 4. I'm going to graph those. Now, it's important to note that this 0 is in conflict, but I have the equal to. Because I have the equal to, this has to be a closed circle, which you see right there. Has to, because of the equal to. Now let's do our h of x. Square root of 0 plus 1 is 1, so I'm going to get the coordinate 0, 1. But again, that is going to be open because it doesn't have the equal to. And I can move on. 1 plus 1. Square root of 1 is 1, plus 1 is 2, so I get the coordinate 1, 2. And then square root of 4 plus 1, square root of 4 is 2, plus 1 is 3, so I get the coordinate 4, 3. So my piecewise function would look something like that. Again, open circle and closed circle. The reason that one has to be open, one has to be closed, is this idea of the vertical line test. If they're both closed, it wouldn't be a function. Where is the graph discontinuous? So if I were to write my pencil, did I ever have to pick up my pencil to keep tracing the graph left to right? Yes, that would be at x equals 0. We have what's called a jump discontinuity because I would have to jump up here to get to the blue equation. There are three major types of discontinuities. Jump we just talked about. I'm going to flip back a couple slides here. We have what's called the asymptote of like the reciprocal function. Let me find it. Shoot. Right here. This asymptote, this line I never ever cross. And then we have what's called a whole discontinuity. A whole discontinuity would be something like y equals 2, x plus 4, x plus 4. Now, mathematically speaking, we can cross these out. So when I go to graph it, it might look something like this. Except, technically speaking, x cannot equal -4. So it would have an empty hole right there. So it'd be the whole discontinuity. Thank you for listening, and I hope you have a great day.